Thank you very much for the introduction. Hi, everyone. I'm Evgenios. I'm graduating from Brown University. And I work on leakage abuse attacks and mitigations on encrypted databases. And I'm going to present to you our work on k-nearest neighbor queries. And this is joint work with Babis from Maryland and Roberto, my advisor, from Brown. There you go. So k-nearest neighbor queries appear in a lot of modern database management systems. Here you see some examples, as well as popular cloud services. But in this work, we are interested in one-dimensional k-nearest neighbor queries. So the setup is the following. Suppose you have records denoted S0 to S5, and each record has a value associated with the record, V0 to V5. Now, when a query comes in, Q, and it requests for the three nearest neighbors, the three closest values are V1, V2, and V3. So the response of the query is the set of the associated records S1, S2, and S3. Now, a key concept for our attack is the notion of Voronoi diagrams from computational geometry, so bear with me while I introduce this concept. All the queries that land in between these two white vertical segments have exactly the same response, S1, S2, S3. This is not a coincidence. These vertical lines are the bisectors. Specifically, the first one is the bisector between value 0 and value 3. You can verify this visually by taking the middle of V0 and V3 and see that this line is right in the middle. And if you generalize this idea, you get a partition of the space, which means that each segment corresponds to queries that have exactly the same response. These segments are called Voronoi segments. The vertical lines are called Voronoi edges, and this overall construction is called a Voronoi diagram. For the encrypted search setup, we have a client that outsources his encrypted database to the server, and then later on asks encrypted queries to the server, and the server responds. But for the sake of our talk, it's enough to do the following abstraction. The attacker is the server. So what the server sees is a series of tokens and responses. So the token is generated as follows. The query, again, this gray point in the slide, goes through a pseudorandom function, PRF, with a private key that only the client knows. It's sent to the server. The server uses this token to find the encrypted records that should be returned back to the client. But since our adversary is a persistent adversary, he sees a series of these type of transactions, so it looks like this. Let's see what the adversary can infer from this source of information. The adversary can first see that the two tokens are exactly the same, specifically the first and the last. This means that the underlying query is the same. This is called search pattern leakage. Another observation that the adversary can make is that an encrypted record participates in multiple responses. This is called the access pattern leakage. And in our paper, we focus on two adversarial goals. The first one is called exact reconstruction, where the adversary, using this access pattern leakage, tries to infer the underlying plain text values of the encrypted database. And we study two setups, the ordered responses, where each response is ordered with respect to the proximity to the query point. And we show an attack that is successful when all encrypted queries are issued. For the case of the unordered responses, interestingly, we saw that this is impossible. And the reason is that there are many reconstructions that are valid for this particular observed leakage. The second adversarial goal that we study is the goal of approximate reconstruction. Here, we have again the ordered and the unordered case. For the ordered, we present an attack that reconstructs approximately the underlying plain texts. For the unordered case, we saw that even though we have an impossibility result from before, we can still approximate with a bounded error. For the remaining of the talk, I'm going to focus on the unordered case. Let's see first the assumptions of the attack. We assume that the adversary knows the boundaries, that all the values are in between alpha and beta. We assume that the database is static, that is, no insertions or deletions of records. And we also assume that the client issues queries uniformly at random among the space. For the exact reconstruction, the best case scenario for the attacker is to infer the Voronoi diagram. That happens when all encrypted queries are issued. And we saw that even in this very good case for the adversary, it's still impossible to achieve exact reconstruction. The reason is that here is a valid reconstruction that respects the Voronoi diagram. Again, you can verify that the bisectors are in between the corresponding values. So far, so good. But here is another valid reconstruction that also respects the reconstructed Voronoi diagram. In other words, the adversary cannot really pick among these multiple choices of valid reconstructions. But let me explain to you how we constructed DB2 from DB1. The goal is to keep the bisectors exactly where they are while moving the values. Let's focus first on the bisector 1.3 and 3.5. And for simplicity, let's just move the values as they are down to the second DB. Now, the second task is to focus on bisector 0.2 and 2.4 and move the values. In order to keep the bisector exactly the same spot, we're going to move the values by the same amount towards each other. But if we do that, then 4 should move towards the opposite direction, and the overall movement looks like this. So now we have exactly the same Voronoi diagram, but a different reconstruction. You can apply this technique and construct multiple reconstructions, which means that the adversary cannot really tell which one to choose and cannot achieve exact reconstruction. So from the adversarial point of view, it looks like we just hit a wall. Since there are many reconstructions and the exact recovery is impossible, the encrypted values must be safe, one might think. Unfortunately, this is far from the truth. In our work, we saw that we can still approximate really well the underlying plain text values. As I said before, in case all queries are issued, what the adversary learns is the length of its Voronoi segments, in other words, the location of its bisector. For simplicity, I'm going to assume that this is the case for the remaining of the talk, but in our work, we saw that the combination of the uniform query distribution assumption, as well as standard concentration bounds or multinomial distributions, are enough to approximate this quantity. The goal is, through this characterization, we will understand much better the space of valid reconstructions, and the hope is that using this intuition, we can reconstruct with the guarantees. So the key idea for our approximate reconstruction attack is that we use the geometry of the bisectors to define unknowns. What I mean by that is the following. Let's focus on the red values V0, 2, 4, 6, and 8. Since the geometric property of the bisector is that it's equidistant from the values, we will define as an unknown the offset xi0 of the value from the bisector. Therefore, the value unknown plain text value V0 can be expressed as the known location of the bisector minus the offset that we just defined, xi0. Similarly, V2 can be defined as the known bisector plus this offset. If we keep doing this analysis and substitute the derived expressions, we can show that half of the values can be expressed as a function of the known bisectors and the unknown offset. But we used just one unknown here. We can apply the same trick for the remaining of the values by defining a new unknown xi1. Overall, using this trick, we reduce the space of reconstructions from n dimensions, where we would have one unknown per plain text value, into a space of 2 dimensions by just having one unknown per offset. And this is really important because if we're trying to break a database with millions of records, instead of trying to understand a 1 million dimensional space, 2 dimensions are enough. But this offset cannot take arbitrary values. It has to follow certain constraints. We define the ordering constraints that guarantee that value 0 is going to be less than V1. So we plug in the algebraic expressions from before, and what we get is unknowns on the left-hand side and constants on the right-hand side So you see the xi's on the left, but more intuitively, the geometry looks as follows. We have on the x-axis xi0 and the y-axis xi1. All the orange-colored offset assignments satisfy the ordering constraint that you see to your left. If you apply that to the remaining ordering constraints, that is v1 less than v2, 2 less than v3, what you get is a rectangle where, again, all the internal points satisfy the ordering constraints. We define one more set of constraints, the boundary constraints that satisfy the property that we won't have values outside the boundaries. But overall, we get this really nice-looking polygon right there. So the main idea is that we managed to squeeze a seemingly large space of valid reconstructions into a small polygon by taking advantage of the geometric properties of the problem. So what you saw before in the impossibility result, the value assignments now map to dots inside this polygon that we constructed through the unknowns that we defined and the constraints that we defined. Let's define the error now. Let's assume that the original database is v prime and the reconstructed database is v double prime. And this is the polygon that we're familiar with. The error in our work is defined as the maximum absolute distance between any value, original underlying plaintext value, and the reconstructed value. And in our work, we show that this is upper bounded by the diameter of the polygon that we define. Diameter is the maximum Euclidean distance in the polygon that you see there, and it's indicated with this white dotted line. But one nice property is that if you draw a circle that uses this white line as a diameter, then you have the property that all the points of the feasible region are inside the circle. Therefore, all the feasible region points are at most diameter over 2 away from the center of this circle that we just drew. And this is exactly what we return in our reconstruction attack. We approximate the Voronoi diagram, we define the constraints, we construct the polygon, construct the circle, and output the center of the circle. And the guarantee that we give is that in the worst case, our reconstructed v double prime is at most diameter over 2 away from every database, plaintext database of the feasible region. Of course, this exposition is based on the premise that the client is issuing 2 nearest neighbor queries, but this idea can scale for higher values of k. For instance, if you focus on k equals 3, then its constraint, it's a half space in the 3-dimensional space. So now you want the intersection of half spaces, and the result is this polytope that you see to your right. We ran our attack on a real-world dataset with a geolocation of a German politician Matt Spitz. And here you see his whereabouts for the month of October in 2009. As you may notice, this is a 2-dimensional dataset, and our attack concerns 1-dimensional data. So what we did is we used standard techniques from the database community called space filling curves that reduce the dimensions from 2 to 1 in order to mount the attack. We reduced the dimensions, we simulated the access pattern leakage that I showed you before, and we mounted the attack on unordered responses. And the result that we got looks as follows. As you can see, there is great resemblance between the underlying unknown plaintext values to the left and what we reconstructed to the right from the access pattern leakage of the encrypted database. And in terms of numbers, what we saw is that even when we increase k, 2, 5, and 8, the absolute error stays really small. Absolute error is 1 to 1.4 in a space with 160,000 potential values. So the reconstruction is really accurate. One other interesting observation is the success column there. We deem our attack as unsuccessful when the approximation of the constraints is not good enough so as to have any feasible region at all. And as you can see, even in that case, we have high success rate. Another interesting observation is the notion of the diameter, which is a key concept for the quality of the reconstruction. Here you see that even in this real-world data set, the diameter stays really small, ranging from 2 to 13, which means that the quality of the approximation is really, really good. So overall, I introduced the first leakage abuse attacks on k-nearest neighbor queries. We studied the adversarial goals of exact and approximate reconstruction. Whenever it was possible, we presented an attack that approximates the underlying plaintext values really well. And whenever we fail, we provide any possibility result. And that concludes my talk. Thank you very much.
We have time for several questions. State your name, maybe.
Ellie Canal, Software Engineering Institute, Carnegie Mellon University. That was very interesting, thank you. So I noticed two things. In the example attack you gave, many of the points were very close together, and you seem to have a large number of them. I don't know how that looked in the transform data set, but I'm curious if there's constraints on both the size of the data set and the distance between the points.
Yes, so that's a great question. In our work, we show that when values are close, the underlying plaintext values are close, the diameter is small, which is both good and bad. It's good because if we manage to approximate, it's going to be a really good approximation of the underlying plaintext. But if we fail, it's because we didn't see enough queries so as to build an accurate feasible region reconstruction. But definitely, the closeness of the underlying plaintext values plays an important role both in the success and the quality.
Thank you.
Thank you.
Hey, Paul Grubbs, Cornell University. Nice talk, Evgenios. I was just wondering if you had any thoughts on what could be done without search pattern leakage?
Without search pattern leakage?
Yeah. Like just access patterns.
Yes. So for the sake of this presentation, I presented the discretized version, but our attacks work even if you have the continuous values. And in this case, you don't know whether you saw all the possible queries, because that was one of the underlying kind of themes in my slides. But even in that case, you can still mount the attacks successfully for this particular type of attack. Thank you.
I had a question about
Yes.
the space filling curve.
Yeah.
So in higher dimensions, isn't it going to be the case that points that are actually close are going to be far according to your space filling?
Yes, you're right, you're right. So space filling curves approximate the distance. And there are some works, well, there are a lot of works, that study how well these approximations work, but that's not a concern of our attack per se. We focus on this one-dimensional setup, and for the sake of the demonstration, we just use space filling curves to mount it down to one dimension and mount the attack there. But you are absolutely right that there is an interplay between the quality of the distance approximation and the dimensions of the space filling curve.
Let's thank the speaker again.